Hello and welcome everyone back to my another second tutorial part about transformers. And in the previous part we already covered a little bit about transformers. This was some kind of introduction to it. We got familiar with them, what they are and what advantages and limitations do they bring. Also, we started implementing it in TensorFlow by going step by step. So we implemented the positional embedding layer, and if you want to follow it, you can find the link in the description below this video. I suggest you get familiar with the first part before continuing on this part, because it's very relevant to know what happens in the first part and what we covered there. I'm talking about positional embedding layer. That's kind of crucial and essential for understanding the transformers. So the link is Power Lessons Transformers Introduction for this tutorial, and right now we can go back to my tutorial. So basically you might see right now that transformer architecture I'm showing you to remind you a little about it, and in this tutorial series we're gonna understand it step by step what it does and what each part means. So in this part we will implement the add and norm layers, base attention layers, cross attention layers, global self-attention layers, coastal self-attention layers, and feed-forward layers. As you might see, that's kind of main parts of whole transformer. And later we're gonna join them into a whole encoder and decoder blocks. So mainly in this tutorial part, I'll focus only on the attention part, add norm layer and feed forward layer. So we'll begin from this add a norm layer. If you pay attention to transformer architecture, you might notice that this layer is after each attention layer. This layer is responsible for adding the residual connection and applying layer normalization. The transformer model utilizes add and norm block to facilitate efficient training. These blocks incorporate two essential components, a residual connection and layer normalization layer. The residual connection establishes a direct path for the gradient, ensuring that vectors are updated rather than entirely replaced by the attention layers. This helps the gradient flow during training. On the other hand, the layer normalization layer maintains a reasonable scale for the outputs, enhancing the stability and performance of the whole model. The transformer model has strategically placed these add and norm blocks with corresponding custom layer classes defined to handle them. To ensure a proper propagation of TensorFlow Keras masks, the implementation employs the add layer instead of simply plus operator alone, which doesn't handle mask propagation. So in summary, these blocks are crucial in the transformer model, ensuring effective training by incorporating residual connections and layer normalization. Custom layer classes are utilized to handle these blocks with the add layer, addressing mask propagation within the implementation. So we'll not create a separate layer for this addition and normalization functionality. Instead, we'll create a base attention and feed forward layer that will handle these for us. So let's move to the base attention layer. The attention mechanism is the core component of the transformer model. It enables the model to focus on the relevant part of the input sequence when processing each token. This is achieved by calculating the attention weights between each token's query and key vectors in the sequence. The attention weights are then multiplied by the value vectors to obtain the context vector, which is the output of the attention layer. So we'll implement all the attention layers used in transformer model. But first we'll create a base class for all attention layers. These all are identical except for how the attention is configured. Each contains a multi-head attention, layer normalization, and add layers. We can create a base class that takes care of all of this. The only thing we need to do later is to implement the call method in our object. We can begin by creating a basic class that includes the necessary components layers to implement the attention layer. And each specific use case can then be implemented as a subclass of this base class. Although this approach requires writing a bit more code, it helps maintain clarity and ensures that the purpose of each subclass remains apparent. So already have this implemented layer to save my and your time. And within the class, there are three essential layers. So this is the multi-head attention, layer normalization, and add layer. The multi-head attention layer computes the attention weights, which determine the relevance or importance of different parts of the input and output sequences. The layer normalization layer normalizes the layer's activations, ensuring they have a consistent scale across batch and future dimensions. And the add layer incorporates a residual connection. It adds the output of the multi-head attention layer to the original input sequence, allowing the model to retain information from the initial input while incorporating the attention-based updates. We can reuse the code and easily create different attention mechanisms by creating a base class that includes these layers. This is achieved by inheriting from the base class and specifying the unique implementation detail for each specific attention mechanism. This approach aids in maintaining code organization and clarity through the implementation. But still, you might ask how it works actually. And attention layer has two main inputs. It's the query and the context sequences. The query sequence represents the sequence we focus on, while the context sequence is the one we seek information from. The output of the attention layer has the same shape as the query sequence. The operation of an attention layer can be likened to a dictionary lookup with some distinct characteristics. Like a regular dictionary, a query is used to search for relevant information represented by keys and values. In a standard dictionary, an exact match between the query and the key is necessary to retrieve the corresponding value. However, in the attention layer, the match does not need to be exact. It can be fuzzy or approximate. For example, if we search for the key species in the following dictionary, as you can see, the best match might be the value pickup, even though the query and the key don't match perfectly. In an attention layer, multiple values are combined based on their similarity to the query rather than returning a single value. And each component, I talk about query, key, and value, in the attention layer is represented as vectors instead of using a traditional dictionary lookup. The attention layer calculates an attention score by comparing the query and the vectors. The values are then combined by taking a weighted average where the attention score determines the weights. In the context of natural language processing, the query sequence can provide a query vector at each position. In contrast, the context sequence serves as the dictionary with the key and value vectors at each position. Before using the input vectors, the multi-head attention layer employs dense layers to project these vectors. And this is hidden inside this layer, but we don't care. That's the reason why they're hidden. And we'll use this kind of base attention class to create three another classes. This is cross attention is used in decoder and encoder attention, the global self-attention that's used in an encoder self-attention, and causal self-attention. It's used only in the decoder self-attention. So before going forward, let's go back to my base attention and run this code so it will be rendered and held in memory. And now go back to my cross attention layer. The cross attention layer is to calculate the attention weights between the encoder and decoder. In the following image, you might see where the left side goes to the right side, these kind of arrows, and on the left side is encoder and on the right is decoder. So the query vectors are taken from the decoder, while the key and value vectors are taken from the encoder. Using this method, the decoder can concentrate on the essential sections of the input sequence while producing a token for each position. So when implementing this layer, we pass the target, the expected transform result, sequence X as the query, and the context input that is input to encoder sequence as the value and key. As you may see, I implemented this kind of cross attention layer, and there is only X and context, and I tried to write a documentation for it, so it will be kind of self-understandable when you open this kind of object to understand what is what. So that's great, and this means that I almost finished with this cross-attention layer, and we'll test it. To do so, we'll create a simulated random data that we pass to the positional encoding layer and then to cross-attention layer. So first, let's initialize this cross-attention that inherits BaseAttention, and let's create this and we'll test it. And for testing purposes, I'm creating a random data that would simulate some kind of translation task. So usually we have vocabulary sizes, and we define the D model that defines the depth of our model. So first, what we need to do is create the positional embedding layers, and we do so. And then I'm creating a random encoder and decoder data that would match following shape, and we'll input this into this cross-attention layer. And for this purpose, I first gonna run this, and you might see that what is the output of these encoder and decoder embeddings. As you might see, our input was 1 to 100 integer values. That's, for example, from 1 to 100, and these kind of values are vectorized. This means that right now they have additional vector 512, and they are scaled between 0 and 1. And this kind of information represents the input to our cross-attention output. And because this kind of architecture, this cross-attention wraps the encoder and decoder attention, both of these should be inputted. Usually, these encoder embeddings would come straight from the encoder layer, and decoder embeddings would be from below decoder attention layer. But you'll understand this in a moment when we come to these attentions. So that's it about this kind of attention. You might see the output. This means it works. So let's move to global self-attention layer. The global self-attention layer is responsible for processing the context encoder input sequence and propagating information along its length. The global self-attention layer allows each element in a sequence to easily access all other elements with minimal effort, and all results can be calculated simultaneously. To implement this layer, it's crucial to supply the target sequence X as query and value arguments to the multi-head attention layer. So here's the code I wrote for this global self-attention, and it's pretty simple, and also it inherits the BaseAttention object, and that's it. This mechanism calculates a weighted average of values based on the similarity between queries and the keys. The attention scores assigned to each value determine its importance. In simple terms, the multi-head attention learns to focus on different parts of the input sequence, allowing the model to extract relevant information for a specific task. In the case of global self-attention, where the input sequence serves as both the query and the key, it captures the relevant relationships between each position and all other positions in the sequence. And we can visualize this process as follows. As you can see, here comes the key and value from encoder and query from encoder. They all are shared, and this is how it works, and we get a single output. And this block is mainly on the input of the encoder layer. So we'll see about that. So subsequently, the output of multi-head attention is added to the original input. This result is passed through layer normalization, stabilizing the training process and enhancing the model's performance. Ultimately, its normalized output represents the final output of the attention layer. So right now I'll build this object. I run this, and now, the same as before, I wrote a simple test code to test this block. We run the forward propagation to it. And here, as before, I'm creating the encoder embedding layer. I'm creating the random inputs. I create the vector for the inputs from this encoder embedding layer. And this stuff I pass into global self-attention layer. And let's see what output we get. Where it is, here it is, yeah. And as you can see, it's exactly the same as our input. That's the main idea of the encoder. So now let's move to causal self-attention layer. This layer is responsible for processing the target, the decoder input sequence, and propagating the information along its length. The same as it was for global self-attention, but instead this one is for decoder block. And this layer operates similarly to global self-attention, of course, allowing each sequence element to access all other sequence elements with minimal operations and resulting in parallel computation of all outputs. But the causal self-attention layer differs from the global self-attention because it prevents leftward information flow. It's better to see in this kind of image. In the decoder, masking is crucial in the process as it prevents the model from attending to future tokens during training. This masking process is illustrated here, and we are masking simply, for example, if we are giving a sentence, hello, how are you? And when we are feeding to this kind of information to this layer, we don't want to see the last word. We want it to predict the last word. That's a simple example. That's how it works. We simply need to mask some parts of the information. So that's it, and we can, as before, create this one, build this layer, causal self-attention, that inherits everything from BaseAttention. And you might notice that this layer is very similar to global self-attention layer. The only difference is that this layer uses a causal mask to prevent the decoder from attending to future tokens during training. As before, let's test this layer. To do so, we'll create a simulated random data that will pass to this positional encoding layer and the causal self-attention layer, just like before. And of course, I have all the code prepared already for us, and we can run this. And let's see what's the output. You can see that I made some difference here about this masking to know whether the output will be the same or not. So here I simply check the shapes, what the decoder gives as output from this causal self-attention layer. And here I'm simply passing the random decoder input, and the difference is here that I crop the data before passing it to the decoder embedding layer, and here I crop the end of the sentence after feeding this to decoder embedding layer. And the idea is that mask works exactly the same, and our results are actually the same. So as a result, we should get 0 when we subtract one output from another. And that's exactly what we get here. We get zeros. So there is no difference between these two approaches. Only difference would be what is more efficient for us. So this would require different testings, but that's not the idea here right now. We simply want to implement these layers and know how it will work. So that's it about these attention layers, and the last part left is to check what is the feed-forward layer and how it is implemented. Looking closer at the encoder and decoder layers, we can see that there is a feed-forward layer after each attention layer at the head of these kind of encoder-decoder blocks. So this layer comprises two dense layers that are individually and uniformly applied to every position. This layer is primarily used to transform the representation of the input sequence into a more suitable form for the task at hand. This is achieved by applying a linear transformation followed by a non-linear activation function. And the output of this layer has the same shape as the input, which is then added to the original input. So I already implemented this kind of layer. We can run this, build, and that's it. And as you can see, here are the dense layers, add, normalization, or etc. And then we simply how the forward propagation is done. We run it through the dense layers, then we add, normalize, and give it as output. That's it. So we will use the same random input as before. The output shape should be same as the input shape from this. So the same as before, I already created this testing code for us, and simply we create random data. Then we feed it through the positional embedding layer, we check the shape, and then we feed it through the feed forward layer, and it should be also the same. So let's run this, and at the output we can see that it's actually the same. So that's the idea here. It simply applies the dense layers and normalize it later, and that's nothing so magical done here, and that's pretty simple. So that's it about these layers. Now you have some kind of basic understanding how this attention works, what is the feed forward layer, and what is add and norm layer, and how they are connected together. And right now, when you look at kind of this architecture of the transformer, you should start getting to understand how they connect with each other, and why I was checking the output shapes of each of these layers, so I would know that they would be compatible when we connect them together. So that's the main idea, and you might see that it's nothing magical about these attentions. They are pretty simple. They are implemented in a very straightforward way in a different blocks and etc. So it would be very simple to implement them. So that's it about this. We covered the attention layers, these kind of all the blocks we needed. We covered previous tutorial positional embedding layer, and right now we've finished all the blocks to cover. So that's it about this tutorial. In next part, I'm thinking that it's about time to connect these into a whole encoder and decoder blocks that later we're gonna join into a whole transformer model that we'll use to train. So that's it about this tutorial. I really appreciate that you watched this until the end. If you like this, please smash the like button. You subscribe this channel. If you have any questions, notes, or etc., you can leave them this message for me in the comments below, and we'll see you in the next tutorial. In the next part, I will build the transformer model. Well, not sure about transformer, but definitely we'll build encoder and decoder layers. Well, that's it about this, and we'll see you next time. Thank you again for watching, and we'll see you next time. Bye.